Everyone's happy, except remember, statistics is going to come back into this over and over and over again. There's no way around it, and now it's going to be embedded. Now there's no excuse that I didn't know how to. So if you're having trouble doing any of these activities, please see me. You're in my study hall, you can ask me. We can sit here quietly and go over it, or we can do it after school on Wednesday or Thursday. So remember, Wednesday and Thursday, I'm available if you need to get extra help or different resources that we don't have in class. But if you don't need it, that's fine. So there is tutoring on Wednesday and Thursday after school from 3 o'clock to 4 o'clock p.m. Those are, you might, for lack of a better purpose, we'll call it office hours. That's when I do chess club as well and D&D club. So if you're coming in for tutoring, make sure I know it so that we can find a quiet spot, a space to do it. All right. That being said, this week there's going to be some. I already put it in your handout that I gave you, but I'm going to remind you now. Your homework is all in there for the week, for next 3 weeks. Not all of it, but most of it. Anything not in there is going to be. Let me rephrase that. All your homework is in there for the next 3 weeks. There will be projects that might require you to overlap with some out of class time. Everything's going to be scheduled or planned to work within the period. But if you take longer, you need more time, that's on you. But understand, it does not, gentlemen in the back, that does not take away from your homework responsibility. So everything I plan is planned to be done in class unless it's homework. Is that clear? But if it takes you longer, then it takes you longer. That's on you. Is that understood? I'm willing to accept it late, but you need to be willing to have to manage the idea of having to do both homework and then the extra work that you didn't get done in class. So use your time wisely in class. Tomorrow, you're going to have a online lab that will cover Chapter 2. I will not be here, but that lab will need to get completed. Let's say lab/activity, because I never really like to call these labs really, but they're lab/activity. You will have to manipulate data. You will have to insert stuff. That will be due by the end of class. Look, in Schoology, bless you, it will not be accepted late. If it's incomplete, it's better you turn it in incomplete than to try to argue that it needs to be, you did to do that or something else. If you have an excused absence, obviously, you can submit it afterwards, late. I mean, I hope that's obvious, so I can feel the tension when people are like, no, it's a 0. Some people will be absent. I'm going to be absent tomorrow. Obviously, that's what I'm giving it to you, obviously. On Friday, I also will be absent. There'll be another activity/lab on Friday. Again, due at the end of the period. I know there's a senior function. I know seniors have something to do. That's fine. Get it done, but also get this turned in. If you're absent, you have 2 days for every 1 day you're absent. So that means if you're not turning in on Friday and you're absent with a blue slip excuse, right, or a note from the office, then you can turn it on Monday. Is that clear? Otherwise, it's a 0. And by the way, you guys are doing a fantastic job keeping up with your work. And it's I would always if I were you, I would always choose to turn in bad work rather than no work at all. Better turn in half-done work, excuse yourself later, and then redo it and resubmit it, than to turn in nothing and have no evidence that you've done anything in class. Okay, so that's tomorrow and that's Friday. Today we're going to start going over the chemical content of life. You have in front of you a chapter study guide for the chapter reading. It should be stuff you already know. All of you have had chemistry. Some of you have had AP chemistry. All of you, I believe, have had at least one biology class. But a lot of this you might have forgotten. And there's a lot. But you need to review this. And this is your study guide. I'm going to now start teaching this.
This is due tomorrow?
Is that what I said? I didn't say any due date yet. So I'm going to start talking about this, so let's start talking about it. So I think we've all, who knows the story of the atom? Does anybody, I would argue that, I would expect that Owen knows where the word atom originated. I expect this because Owen studied Greek philosophers. Atomos was the form of the word, yeah. But what was it? What's the idea? What was the idea? Indivisible, yeah. So, what the ancient Greeks came up with an idea, they were wrong, but they came up with an idea, which is still where we get our word, about the atom. And their idea was, look, if we take this stuff, whatever this stuff is, and we keep dividing it in half, and in quarter, half, and half, and half, and half, and half, and half, and half, eventually, they argued, that thing, there'd be a thing, that thing, you couldn't divide it. It's the smallest particle. And they thought, let's call it the atom, the indivisible, the thing you could not divide, the smallest thing. We know it's not true anymore. That's where we get our nuclear bombs, right? Because we split the atom. And if we do that, then that causes a boom. So it's not indivisible, but it is the smallest particle that we have to deal with on a daily basis. There are smaller particles, right? An atom is composed of things. But they thought an atom was the smallest thing. Moving forward, today we know that there's around 118, there's more, plus different kinds of atoms. Right, so there's about 118. There's more now. I think they come up with a few. Some of them only last like a split second before they disappear, but. (118) different kinds of atoms. Fast forward, the Greeks and Romans, and then in the Middle Ages, and even there were these people in the Middle East as well. They were trying to change lead into gold, and these people were called alchemists, and their idea was let's take magic. They believed in magic. The magic. You said you accept magic or you don't accept magic?
No, I was just repeating.
So magic.
So that's not how you spell magic.
It's with a G, I know.
What magic?
Magic.
Whoa.
Wow. Okay. Magic and science. And I'm going to put this idea of science in quotation marks because it didn't exist then. Science is something very specific. Look, it's hard to write and talk and look at you all at the same time. So science, they mix the two together. And so they would come up with chemical formulas. They first started to divide the substances into smaller and smaller parts. So they would take ore, a rock they'd find, and they would dissolve it in various compounds. They had this stuff called lye, which today we would call a base. You might call it, if you've heard of lye, something similar to lye. See, again, talking and writing at the same time. Lye is a base, and it's a very strong base. It's actually a hydroxide. You've heard of this. A substance like lye you would call Drano. So it dissolves a lot of stuff, right? They also had acids. They could find acids, and they would help dissolve them. So they could dissolve them in acids, in bases, and in water. And they would use all three to kind of dissolve and try to separate them as best they could. They would use temperature. They would use temperature, and they would use then the ability of things to float on other things to separate them. In fact, they got these ideas from what the metalsmiths, when you look at the great metalsmiths of the Middle East, Damascus steel. Have you ever heard of Damascus steel? Damascus, you know where Damascus was? Where was Damascus? It was Syria, around Syria. I mean, the countries were different then, but Damascus was, the word Damascus, the city was around for a while. So they would use the smiths tinkering. They would practice. They would try things that didn't work, and then they'd try something else, and it worked, and they taught it to their apprentice, and then their apprentice to their apprentice. In India, the great Indian empires did something similar. And they would separate these different colors and different substances into different components, and they would measure, and they would write down these formula. They would write these formulas down, and they had these alchemy, and they called it alchemy, and so they were alchemists. Their whole intent in doing all this experimentation, it was experimentation. Yeah. Karma. They would take these, they would do these experiments. They weren't experiments the way you and I know experiments today. They didn't use control groups, they didn't use experimental groups, but they did record data, and they did see what worked. They had two bins. They either had a fail bin or they had it worked bin. That's it. And they wrote, if it worked, they kept it. If it failed, they threw it out. And they kept doing these experiments over and over again. They talked and they wrote books, and it was all in secret. And they would do little magic incantations along with everything else. See, they didn't understand energy, right? So when they mixed two things, when they mixed an acid and a base together, and it bubbled and formed heat, they didn't know what happened. What else could it be? I'm sure I could foresee a Middle Eastern alchemist sitting and mixing two powders and getting a poof and some light and thinking a jinn just appeared. Because jinns were real in their minds. They were real things. I don't know why this is funny. This should not be a topic of conversation. It's literally, that's how people thought back then. People thought about spirits and demons and jinns were real. There was not, gentlemen, ladies, it was not a joke. That's what they thought, they were real. It was real. That it was as real as today as whatever it is you believe in. Like, it was as real as it is, as everything as electricity is today. They thought that's the way the world worked. When you look at some of the ancient Greek philosophers, when they saw things move, they felt they had a spirit moving them. There was literally a spirit pushing them around. They looked at the stars and the planets moving. They thought there was a spirit moving the things in the heavens. My God, the Egyptians thought that Ra was pulling the sun around with a chariot. The same with the Romans and Apollo. Everything had to, if things moved, they had to have what the Greeks called animus. There had to be something that moved it. What moved it? A rock fell. What moved it? They didn't understand every action, for every action there's an equal and opposite reaction. They didn't understand that. How could they possibly understand that? Nobody broke it down. There was no systematic way of understanding the world. When you saw rags in the barn, you left some rags in the barn, the next day you saw mice, what did they think? What did they think? The rags turned into mice. They literally thought that. For years, people thought that. You could even have it in our old wives' tales. Don't leave rags around because you'll get mice. Don't leave crumbs around because you'll get whatever. It was not a thing. When the word men, when we talk about sperm with men, do you know what most Western, and I don't know about the Eastern cultures, but I know the Western culture individuals would call what the men's sperm? Seeds. Men spread their seed. They called it seed, implying that men had everything that was necessary to plant and grow, that all they needed was a field to plant. The idea of having half the DNA and then the female has the other half, and then together you form an embryo, that was not in their heads. They could only think of planting. What they did, they planted seeds. Guys, before science, people used what happened every day as their experiences. Throughout Europe, people would leave food out for the elves and the fairies, because they did not want them evil fairies. They wanted the fairies not to invade their homes. Knock on wood. Was to scare away evil spirits. Evil spirits is a real thing, even to this day. Most people believe in this stuff. It's not anything, it's not a shock. It shouldn't be a shock to you that people think this way, because people still think this way. Okay. So these alchemists, their big goal was to try to find, they were able to get this stuff called lead. And man, they said lead is heavy just like gold. Lead is heavy. Gold is heavy. If you had a brick, you ever see in the movies someone taking a bunch of gold and running away with it? That's not real. Gold, that much gold would be too heavy for that. They'd be moving several hundred pounds. If you had a box full of gold, it would be too heavy for you to carry by yourself. It's a struggle because gold is very dense. And so is lead. That's why we use lead in weights to hold things down. It's heavy. Except it's useless to us, right? It's not shiny, it's soft, it's not shiny. It turns out it causes nerve damage, but we didn't know that back then. But lead is similar to gold, and they thought, wow, we could take lead and we could turn it into gold. That was their whole goal. They didn't do all the chemistry. They did chemistry, by the way. The alchemists were the first chemists. In the Middle East, in Europe, in India, there were alchemists in all those groups. They all communicated with each other. because they all were doing similar experiments. They did not use control groups, so there was a lot of mistakes. But they went back and forth, and they purified a lot of substances. Frankincense and myrrh. And obviously gold was one of the things that the early metal workers purified. But there was all kinds of things that they could get out of this. Dyes. They started getting colored dyes that they could use in clothes. And there was a whole industry. So chemistry evolved from this idea of alchemy. And honestly, chemistry is still a little bit like magic, isn't it? You get so many different changes in colors and smokes and energy. It could easily, in fact, what do magicians use but chemistry to make things poof and flames out of nowhere? So in any case, their objective was to turn lead into gold. How could they do that? They kept trying. They obviously failed miserably, but in doing so, they developed this science called chemistry. Science came along later, though. The science part was when we started weeding out the nonsense, the stuff that literally did not make sense. Today, we can turn lead into gold. And we can. It's easy, actually, to do today. Could someone... Is someone with a computer, an iPad, look up what atomic number is lead and what atomic number is gold. Let's make our little squares. Lead is PB.
Lead is AU.
And gold is AU.
Gold is 79.
Gold is element 79. And what's its atomic mass? I want both. 197? 196.96. So that's really going to be up for discussion right in a minute. And what's the other? What's lead?
82, and then the mass is 207. 207.2.
All we have to do is to make lead into gold is to take away some protons and some neutrons. And with the right atomic experiments, which we can do in an atomic collider, we've done this. They've actually accomplished this. You can take lead and turn it into gold. The problem is it costs more money because of the amount of energy you required to throw a bunch of little. The way we do it is you take an atom, and as you know, an atom is made of. Let's take gold. How many protons? 79, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need 70 of these, so 20. So that's 40. That's 40. And then do one more. One more is 80. You see why it's dense?
Yeah.
And then you take that 80 minus 1 is 79. 79 protons. And then how many neutrons? 79. 79 is what? It's not 79. 79 is 8. It's 158. That's not right. How do I know it's not right? How do you find the number of neutrons? If that's the number of protons, that's easy because number of protons is here. 117. You say it's 117. How did you figure that out?
196 minus
196 or 7.96 minus 79. What you're suggesting to me is that the atomic mass is the number of protons plus the number of neutrons. This should be a review, and I got to go quickly. So if this is not a review for you, if this seems odd to you, you need to come and see me. That then if I subtract the number of protons which is, you know what? Let me just go ahead and write the atomic number here, even though you should know it. Atomic number, which is the number of protons. What should be left? It should be only the number of neutrons. Is that correct? So the goal is to get rid of protons and keep neutrons. So subtract the protons from 196.6. But I don't get a whole number. Can I have a half a neutron or a tenth of a neutron? I cannot. And someone ingeniously rounded up to 197 when asked what the atomic mass was. That was correct. That was the right thing to do. They rounded up, and why up? Because it's 0.96. And when you round, if it's 5 or bigger, you round up, correct? So it's 197. When you subtract from 197.79, what do you get? So it's 118 neutrons. I still don't understand where where that missing neutrons were. What is this number that was written on every periodic table? Almost every periodic table element has a decimal. It's not, in fact, I don't know of any that doesn't. It's not a whole number. Even though I'm telling you it's the protons plus the neutrons, and you can't have part of a proton or part of a neutron. So what's the answer? What is this number? It's the atomic mass. It honestly cannot be what I told you in 9th grade, which is the number of protons and the number of neutrons. It cannot be.
Because
You can have a partial proton. So it must be something else. What is it? Yeah. It's an average. Ooh, statistics again. It's actually a weighted average. It's a weighted average. So you take all the what? What do we call them when they have the same number of protons but a different number of neutrons? Isotopes. You take all the known isotopes, you add them up and you divide by the total. So there must be a 118, or I should say that's not true. There must be a 197, a 196. There might be even a 195. I don't know. I don't know all the different isotopes. Stable isotopes. You can make every isotope imaginable, but is it stable enough to actually exist in real space over a period of time? There are some isotopes that won't even last after you've made them with any measurable amount of time. So we look at the stable isotopes we find in nature, and what if you find most of them, like 90%, are 197, but then you have, maybe, let's say 98% 197, and then 2.5% is 196, and only 0.5% is 195. I'm making this up. This number here represents a weighted average. So when you see 196.96, that means most of the time when you find gold, it's 197. But there is gold that's 196 and 195. It's just not as stable. It doesn't last as long. Does that make sense to you, everybody? So the most stable form is 197. That's what we find in the universe, in the world around us, that we've been able to measure. So that's this number. That's why there's decimals. This one, what do you think the most lead is? 207. There's a way to calculate weighted averages. I'm not going to do that. And I'm not going to draw 118 neutrons here. So you can imagine that. I mean, it'd be easy to put 10 and then do it 10 times, but I'm not doing it. All right. So isotope is a different number of neutrons. This is what it comes down to, that an element is defined by the number of protons, and the isotope is a different form of the element, And we call that the most stable isotope. They're all isotopes. Let's be clear on that. All the forms of that element are isotopes. The most stable one is the one that's represented by the atomic mass. So the atomic mass it tells you which is the most stable isotope. Is that clear? This is only going to become important in carbon dating and other dating in biology. In chemistry, obviously, it's important for various reasons. Yeah.
So what differentiates a stable isotope from non-stable isotope?
How long it lasts. If I'm searching for gold and 98% of the gold I find is 197, I'm going to assume that the 196s and 195s don't last as long. And when I say last as long, they break apart. The internal forces of the atom that hold the nucleus together, the strong force, but believe it or not, it's called strong force, that holds the protons and neutrons together, is in 196 and 195 is not as strong as the repulsive forces, and it breaks apart. It's radioactive, it breaks apart into some other isotope, some other element. Because as soon as it breaks off, if it loses any protons, then it becomes another element. Because how do you change lead into gold? You add a proton, you subtract some protons. Boom, you have gold. All right? All right, so that's isotopes. We'll get back to that, and we're going to look at something later called half-life. Did you guys cover that in chemistry?
Yeah.
Half-life? And there's going to be a way to calculate half-life. You'll be working with that tomorrow, I hope. It depends on which one I find, which activity I assign you. But half-life is this idea, if I start off with some amount, let's just say 1 gram of something, and how long does it take to break apart, let's say, I don't know, let's call it uranium. How long does uranium take to break apart and not be uranium anymore? It's radioactive. We know it's breaking apart. How long does it take for it to break down? It'll break down into something else. It'll release neutrons and protons, and it'll become another element. I don't know what element. I'm not a nuclear physicist, so I don't know what element uranium breaks down into, but it'll break up into something else. It could break down into 2 things. I don't know. But it's going to break apart. But I'm going to leave. It's not all going to break down at the same time. It's going to break down. This atom breaks apart. This one doesn't. When we do an atomic bomb, what we do is we make a big part of it. Not even all of that fissionable material breaks apart all at once. Isn't that amazing? That giant explosion happens with only a very small portion of that nuclear fissionable material actually exploding. It's incredibly insane, the power of an atom. If we break it up, though, it naturally breaks up. How long does it take for it? Somebody unplug this machine. How long is it going to take for it to become half a gram, 0.5 grams of uranium? So half as much uranium as when I started. How long? What's the time period? I don't know. Somebody can look it up, but it's something in the thousands of years for uranium. Yeah, question or a statement?
What if it turns into something else before it is half of the amount?
It doesn't turn all at once. It's like if each of us were an atom of uranium, I start to shake and I blow apart into something and become something else. The rest of you are fine, right? The next thing that happens is she breaks apart and turns into something else, and she breaks apart, maybe he breaks apart. But how long it takes it depends on how strongly the atom is held together. How stable is that atom? And that is about the balance of forces, nuclear forces that are occurring inside the atom. Does that make sense? So the only question is how long does it take for a gram of uranium to turn into half a gram of uranium? Look up the half-life of uranium, somebody. First person to do it, I'll give 10 points.
4.5 billion years.
So, what is it?
4.5 billion.
Oh, billion. Dang, I was so wrong. 4.5 billion years. Yeah, there's going to be some kind of, so let's say about.
59,000.
That's surprising to me. So uranium is 4.5. Look up cesium. Radioactive cesium. How long does it take to...
Can you spell that?
Cesium. Can I spell that?
Yeah.
Don't insult me. No, I'm not playing that. What is it?
Actually, 30 years.
Huh? 30 years.
17, actually.
Yeah, I spelled this close. How did I spell it wrong?
Got it right, actually.
Did I? Oh. So 30 years. Now, why would you think that cesium is less dangerous than uranium? Not weaker.
Because its bonds aren't as strong.
It's going to break up sooner. It's going to go away faster. It doesn't last as long. Uranium's going to be around for... So you have radioactive uranium. It's going to sit there being radioactive, shooting you with little atomic energy bullets for a long time. Where cesium, in general, won't. It depends on which isotope, right? But so there's going to be a range. There's going to be a range because each isotope has its own half-life. All right, so we're going to take advantage of that when we measure how much, if we can figure out how much carbon should be in the substance, and we know how long it takes carbon to break down, and it's an isotope that breaks down. If we know how long it takes to break down, and we find a fossil, for instance, and we measure how much of that particular carbon isotope is left, then we should, by the laws of physics, we should be able to tell how old this thing is. But this only works for very long periods of time. What is the most stable form of carbon? As the carbon is the one we're interested in. So let's take a look at carbon. 12. Carbon 12 is... What is it? What is it? Carbon 12? What is the atomic number for carbon? Atomic number for carbon. And what's the atomic mass?
12.3.
Yeah, so obviously, I think by now it should be obvious that 12 is the most stable, because that average is skewed towards the 12. What about carbon 14? What's the half-life of carbon 14?
5,000.
5,000 years.
Yeah.
Carbon 14, I think 14 is 5,000 years, half-life of 5,000 years, according to the one source that someone just looked up. What about any other carbons? Look up carbon isotopes. Tell me, what are some of the other carbon isotopes? These two guys, you better be looking at carbon isotopes. I'm about to fail you in this class. Okay, I just don't know, because Willie always looks like he's up to something. Do you see how he jumped? Did you see him jump?
It's still set 5,000.
I just looked over there. He jumped literally out of his chair. All right, so give me some other isotope.
It's still set.
Carbon 13 is what? Half-life. Yeah. Give me carbon 13 half-life. What is it? It doesn't, so it's no half-life. It's not radioactive. It has a half-life, but we don't know.
It says it's stable.
All right, so stable. What about carbon? Give me another isotope. 12 is definitely stable. That's the one that stays around the longest.
Carbon 15.
Carbon 15, well, how long is that one?
2.449 seconds.
Carbon 15,
Seconds is 9 months.
say again?
2.449 seconds.
That's how long it lasts?
2.449 seconds. It does. There are some isotopes that will not last very. They're very unstable. Their forces are so unbalanced when they're made, they break apart immediately. Well, at least in 2.499 seconds. Anything else? Any other isotopes? There's more isotopes than just carbon-14. What is it?
11.
All right, carbon-11 is what? 20.31 34 minutes. Is that all the carbons we have?
There's a lot, but all of them are like in the milliseconds and the nanoseconds.
So the only one that lasts a while, as far as we know, from what I hear, is carbon-14.
Yeah.
This is the one that's going to be useful then. These others are interesting, but they're not going to help us determine the age of something. So carbon-14 dating is what we use in fossils. When we look at, it's one of the things we use. There's other elements to look at. All right, can we go on then? We understand this. This is all you need to know. You don't have to understand the actual atomic number. You don't have to calculate forces. You're going to have to calculate half-life. I'll show you how to do that. And activity, we'll move on. I don't think they're even going to ask you to calculate half-life, to be honest, but you should understand how to do it. I'm sure you haven't done it since middle school, if you did it at all. So I think you should get that experience again to make sure you get that in your head. All right, everybody okay with that? Am I okay? Can I go on? Is that a yes, no, maybe? All right, what's a yes? So we made it through the atomic era, and we know what's in an atom. How do we know what's in an atom? Well, this guy named Rutherford did a really amazing experiment. There were several experiments done. I'm not going to go into details because I don't think you need to know details. But there's this thing called a cathode ray tube. I believe you call it a television. This is how televisions used to work. Still, they don't work this way anymore. We have LEDs and all different. But what would happen is that you would take electricity and there would be a gas, an ionized gas, a gas that would change, that would actually light up when electricity flowed through it. And I hope you're paying attention because there was a time we knew that this electricity, we called it a cathode ray tube because it was a tube. And when we connected it to electricity, it created we call it a cathode ray tube. It was a tube that we had an anode and a cathode. We connected it to, and we created a what? You've never heard of something called a ray, like a ray gun? Yeah. Okay, ray guns are what? They shoot these what? Rays. Are rays wiggly? Rays are wiggly? Laser beams are what? Straight. So a ray was straight, and when they shot it through, it was straight. But they didn't know what the charge was. This positive or negative? They knew this thing. There was this positive side, negative side, from their work with magnets, from their work with electricity. They knew there was a positive and a negative side. They could tell because they did experiments. There's a positive and negative side. But they didn't. They asked a question: What are these rays? What is this ray made of? Well, they called it. It was made. They knew it was electricity, and they knew these were tiny little particles. So trons, little trons. What would you call it? It was they're trons made of electricity. Electrons.
Wow.
So they knew electrons existed. they could see them in a cathode ray tube, but they didn't know the charge. Was it positive or was it negative? So they did something that was really cool. They took a magnet, the positive end of a magnet, and they put it in the near the cathode ray tube, and what do you think happened?
Like opposites are attracted, so the things went towards the positive.
So it did this, and then it did this, and then kept going to the positive side. So it got attracted to the positive and did the opposite for the negative. So they said this is negative. That's it. That's it. That's all they knew. Atoms had this, electrons. They knew it. They looked at hydrogen. What do you know about hydrogen? It only has one proton. Hydrogen has one proton. Most hydrogens have 0 neutrons. Most hydrogens are 0 neutrons. So the mass of hydrogen is actually H1, and it's 1.001 or something like that. I don't know, you can look it up. But most hydrogen is just a single proton, no neutron. Sometimes we find hydrogen that's neutral. Not usually. Not neutral. And sometimes we find hydrogen that's positively charged. Hydrogen can be attracted to negative things, so we can identify them as. So we knew a proton existed. We knew that existed. And we can count them. We can count them. I'm not going to go into details of how they can count them. And just by doing, kind of counting up how many protons, we looked at let's say, at a lithium atom. Lithium is what number on the periodic table? Yes, it is 3. And what's its atomic mass?
6.941.
So what are most lithium atoms? 7. So most lithium atoms are 7. So you they knew because of this, they knew this, and they knew this. So they were guessing. There was something else in the nucleus that didn't have a charge. So it wasn't positive, and it wasn't negative. It was neutral. The positive they called a proton. What did they call the neutral? A neutron. Hey, it should be hopefully obvious. I hope you're like, duh. But I ask it on a test, and I kid you not, a third of people get it wrong. I don't know why, but I know why. Because it can be confusing if you just assume you know it and you don't practice it. So neutral, they knew there was a neutral thing called a neutron. They knew there was this thing called an electron. Because all these experiments. Oh, sorry. This negative thing called an electron. Oh, come on. What? Oh my God, I have to find a new app. This app is not, it's not playing well with others. All right, negative is electron, and positive, obviously, is proton. So they knew that, okay? They knew those things. I think everybody's cool with that, right? They knew there was a negative. They knew there was a neutral. I'm just not going to put anything. And they knew it was a positive. But here's what they didn't know. They didn't know how things were organized. Some people thought it was that you had a hard shell of protons and inside were the electrons. They knew they were there to be balanced. Maybe the outside was neutron, the inside were the positive negatives neutralizing each other. They didn't know how it was organized. Some people thought it was a plum pudding model. You've heard of the plum pudding model? It's from England because English people have a lot of puddings and different names, and they have plums in pudding. So you just have like this pudding with these. Imagine pudding. You've eaten raisin pudding, I'm sure. Well, it's absolutely delicious. So I'm sorry you haven't had it. So imagine just a bunch of things stuck in here. 3 different things just stuck in here, just randomly. 3 different things, right? Protons, neutrons, electrons, all in this like a pudding. So there's a lot of these theories. So how do you figure it out? What an atom is made of? And so we have to be able to get in between the spaces of the matter. Which, to do so, we have to get something very, very thin. Very thin. And and maybe I'm wrong about this. I'm going to go ahead and make a statement. The most malleable, do you know what malleable means? Able to be shaped with a mallet. Do you know what a mallet is? A hammer. One of the most malleable substances that we know as human beings is what? Huh? No, water is not malleable because it's a liquid. No. It is a metal. Which metal? Copper's good. It does work well. Silver's good. The most malleable substance we know is gold.
I said that.
I didn't hear it. It's one of the reasons that makes it so precious. We can make it into any shape we want. We can pound it into that very thin shape called gold foil. Gold foil, you can get it down to almost 1 atom thick.
You can eat it, right?
Yeah, you can eat it, but I don't know why people. I don't eat any heavy metals. I don't care that gold is safe. If it's a heavy metal, stay away from it. I'm just giving you a warning. Don't talk to me about it. I know people put gold in their food. It's stupid. It's a waste of money too. On top of it. Huh? It is malleable, but what makes gold so special is it's malleable. It is not corruptible. It doesn't react with things. It's very stable. So it doesn't oxidize. I've never taken my ring off unless I'm in the doctor's office. I use bleach.
You shower with it on?
I shower with it on. I don't take it off. And look, it's not green. It's not oxidized. Doesn't change shape. Doesn't change color. Why? This is why it's precious. This is why gold is so special to us, because it's malleable. You can shape it into a ring or a statue of a calf. Or it's a religious reference, sorry. Or, Moses, statue of calf, God got mad, condemned all the whatever. No. All right, it's a bad joke. Moving on. You can form in all kinds of shapes. It doesn't oxidize easily. It does not react with oxygen well at all. Iron, steel does. It turns into rust. This will last at the bottom. We found gold rings at the bottom of the ocean after several hundred years, encrusted in coral, took the coral away, and it's as shiny as the day it was made.
Wow.
Gold is an amazing substance. So, anyways, so we took this guy named Rutherford, and who it was doesn't matter, made made a gold foil shield. And he needed something smaller, a wave of energy smaller than light. Light was too big. Light does not get in between the the gold atoms. When light hits gold, what does it do? It reflects. It gets bounced back. It's too big. We need something smaller than light. So what we can do is use electrons. We can make electron rays. That's how we got a cathode ray tube. And we could shoot not electrons. My bad. X-rays. Very much like electrons, they get shot in a ray. And he shot the ray at the gold foil. And then on this side, he had, that stuff that they use in your X-rays, a film that changes color if X-rays hit it. So the only time you see anything on an X-ray film is if the X-ray did not go through. The black is where the X-ray went through. So, in any case, how it works doesn't matter. This is X-ray film. So what do you think they expected when they shot this ray to this film? What did they expect to see? Yeah.
Film to be like black because the ray should go through the atoms.
The ray should go. It's going to go through the atoms, but as soon as it hits the nucleus, as soon as it hits some dense part, as soon as it hits something dense, anything, as soon as it hits a proton, if it hits an electron, it probably won't, because they knew electrons were small and almost had no mass. They knew the mass of a proton. They knew the mass of a neutron. And they knew if it hits a proton or neutron, it's going to bounce. But it's not going to bounce if it's an electron. So what did they expect to see? Yeah.
Either refracts or it goes
Excellent. Yeah, it's going to bounce around and it's going to form a pattern that's going to help them figure out what the picture of the atom. As long as they can, use some math. They're physicists and chemists, so they do a lot of math, right? I personally do not understand. And what they got was this. This is what they got. What do you think happened? Interpret these results for me. Some of them bounced this way, refracted. Correct?
Oh, those were the electrons.
Some of these refracted this way. But what did most of them do?
They hit the middle.
They hit the middle. So they knew that most atoms are made mostly of.
I had a question.
Yeah.
So, does an equal amount of rays come out of the other side as went through the
Yes. There are no new rays, and theoretically nothing was absorbed. So yes, good question. So we have to assume that the amount of rays going in are the amount of rays coming out. That is an excellent question. And so what they found was that the atom is made mostly of space. Matter is made mostly of empty space. It gives a whole new definition to the word airhead. So, Mayar.
Whoa.
So, only because you were talking, Mayar, or listening.
Why?
It wasn't only because of that. It's because I get to pick on you a little bit.
All
All right. So, anyways, we found that, but because of that, they had to throw away the plum pudding model, because if atoms were like plum pudding, then it would just hit and bounce back. They actually expected some rays to be all the way back here, and there were some that bounced back here, but not many. Most of the rays went straight through. So that, plus other experiments, they discovered that protons and neutrons are in the nucleus in a very small space, and I mean small. If an atom is the size, if you had an atom, you got to imagine, you have to use your imagination, which requires you to listen, even if you have purple hair. See, I just used the word purple. Did you see her jump? Just did purple. She's very sensitive.
Purple hair.
Yeah.
Person in this whole class with purple
Well, I was talking before that, but you didn't hear any of those words. It's only when I said purple hair did you actually pay attention. So anyways, the point is, if you had an atom, you have to use your imagination now, whose nucleus was at the center of a stadium. An atom whose nucleus was take the headphones off. An atom whose nucleus was at the center of the Cleveland Stadium. The electrons would be on the outside of the stadium. If the nucleus was the size of a baseball, the orbitals of the electrons would be outside the stadium. Everything else is empty space. That's an intense idea, that all the matter in an atom is at the center. Most of the matter in the atom is at the center. The electrons have mass. Okay? The electrons are matter, they have mass, but they're very, very negligible. So if Powell got on a balance or scale, and she weighed, I don't know, 80 pounds, 90 pounds, I don't know, whatever she weighed. I can't tell. If you're smaller than me, I can't tell. If you're bigger than me, I can't tell. I can only tell if you're someone my size. I can't. I would be a horrible person at Cedar Point to tell. And she's on the balance. In fact, you would want me, right? Cedar Point would lose money. So this girl, you know how you get on a balance, they guess your weight? I would lose every time. So she's on a balance, and let's say she weighs 90 pounds, and she's on a balance, and I do this. What's she weigh now? 90 pounds. Would it measure on the balance? If balance, the needle wouldn't even move. You can take it off your head. I don't want to touch it. I would. I just don't want it. Thank you. So that's the same as an atom and its electrons. So that's why we never worry about, when we talk about atomic mass, we worry about protons and neutrons. We don't really worry about electrons. Even though they do have mass, they're so small, we can ignore them, even if there's a lot of them. So we know that protons and neutrons are in the center. We know the protons and the neutrons are in the center. The number of protons do not always equal the number of protons. That is a misconception so many students have in their head. Get it out of your head.
Say it again.
Number of protons and number of neutrons are not always equal. I think it's obvious based on looking at the periodic table, but people don't think about it because you kind of work those problems in elementary school where you have them equal each other. And so that does happen, but it doesn't always happen. Very rarely, actually, is it true? We have electrons. All the electrons are negative in charge. So they have to keep away from each other. They push each other away. That's part of the reason why the nucleus is there at the center, that little dot I just made on the screen. Do you see it? It's right there. I'm pointing at it. It's right there. That's a dot. If that were the nucleus, the electrons would be out here. Oh, yes, ma'am. The electrons would be all the way out here. It's kind of crazy. So these things are called, but we don't want to draw that when we draw it here, when we sketch in these nuclei. So we kind of just drew this. And we say this thing's called an orbital. This is the space that the electrons will allow each other to be in. It is a cloud, and we'll talk a minute about why that is. It's back to why science. It actually is based on exactly what I told you. We can't know anything. But it turns out that these electrons push each other around. And if they get anywhere near each other, their electromagnetic field will push them out of the way. So they can only get so close. That's why the center of the nucleus is that nucleus where the protons are is so far away from the electrons, because the electrons need a lot of space around them. They create these magnetic fields that push and pull each other around. Obviously, the strongest force here is the attraction of the protons. It's pulling them in even though the negatives are pushing away from each other. Yeah?
What are the letter things for the orbitals again?
I'm about to go through them, so give me a second. So the first thing we have, and we're not going to concern ourselves with the details. We're not going to worry about the d orbitals, for instance, because they're not elements in biology that we really need to concern ourselves with too much. Obviously, yes, we do have to concern ourselves with lead and with iron and other things, but we're going to focus on the elements of life in biology for this first year of study. So when we look at this atom, and we look at the first, we call it a shell. The first area, a shell is not actually a shell. It's not anything that exists. It's just a space. It's a space, a definitive amount of space away from the nucleus in which 2 electrons fit. In which 2 electrons fit. It turns out that this first shell, the first shell, can hold 1 orbital, and that orbital is S. S for sphere. S for sphere. It's because we're not certain of where the electron is, we can measure the speed of the electron, we can measure its position. But we can't measure both. So all we can do is come up with a range. And so what we draw is called a cloud. That would be a more accurate drawing of the 1s orbital. First shell, the s orbital, 1s. The first shell can only hold an s orbital. There's not enough space for it to hold any others. Yeah.
So the reason why, could you explain the reason why we draw it as a cloud again?
We don't, because of uncertainty. There's no certain path. The electron could be anywhere in there. This is a probability matrix. This is a probability drawing. This is a drawing by a computer, which in this case is represented by my scribble. A drawing by a computer that tells us electron's probably here, or it's probably there, or here, or there, or here, or there. And this is calculated with some formulas that I don't understand, that there's this little area of certainty where we're going to find these 2 electrons. The first electron is represented by an up arrow. The second is down, and that's because of the spin of the electron. One of the ways the electrons are able, and they call it electron spin. The idea is that because of the field can be somewhat mediated by spinning in opposite directions. So even though they're both negative, if a negative is spinning one direction, the other one's spinning the other direction, they can be closer together. Is it actual spin? I don't know. I'm not a physicist. You can ask any physicist if you want to know. Now, moving away further out, so the first electron orbital is the 1s that can hold 2 electrons. Further, another distance away is the second shell. And in the second shell of this is, again, from the nucleus. This can hold 2 sets of orbitals. 2 orbitals. The first is obviously the s, which again is some kind of random path, right? It's spherical in nature. So it's called the 2s, which can hold 2 electrons. Then there's 3 axes. There's the x, the y, and the z axes. Are you familiar with these?
Yeah.
The z's coming in and out of the board. I drew it here in this direction. These patterns are somewhat odd. They form these dumbbell shapes. This is way too big. they form these kind of dumbbell shapes. Again, anywhere along this going that way, or anywhere along this going this way. There you put one up, here you put one down. When the one's here, the other one's over here. When this one's over here, this one goes there. They're moving back and forth, kind of going in a circle, an infinity symbol. Then this one here is doing this. In three-dimensional space, so understand I can't draw three-dimensional space on this. So another one's going up and down here. Again, one up, one down. And the last one, I'm going to draw it in green just so it doesn't get all muddied, is going along the x-axis. Again, it's a cloud, but as a dumbbell shape. They have dumbbell shapes. Is that clear? These are called the p orbitals. P orbitals. There's 3 of them, x, y, and z. Each one can hold 2 electrons. Do you have to know all that? No, but I think it's important that you have some understanding of this before we start talking about covalent bonds. And I'm assuming, again, that you paid some attention in chemistry. So in biology, the only elements we are really going to focus on is schnapps. It is a liquor. That's why it's hopefully something you'll remember. That's right. You got it. It's carbon, hydrogen, nitrogen. That's right. Oxygen. Phosphorus. Phosphorus. I don't know. Somebody spell it. I don't care. I did?
Yeah.
These guys are making me.
But you could have left it.
Spell it.
O-R-U-S.
For us.
All right. Phosphorus and sulfur. These are the elements you need to know. These are the elements, these are the only ones really that we're really going to concern ourselves with. And of course, there's some others that you're going to really talk about, which is sodium. When we talk about sodium, we're going to talk about sodium ion. We're going to talk about, we're going to have potassium as well, which is going to have potassium ion. We're going to have calcium. We'll talk about calcium, which is a +2 ion. And so when we talk about these are elements. Elements are the smallest component, the smallest piece. Remember the old alchemists broke things down and kept breaking things down? They could break things down, and when they couldn't break them down anymore, they called these things pure. What we call pure today they're the elements. They didn't consider these the elements. What they considered the elements were fire, earth, water, air, and the alchemists of Europe would call it ether. The alchemists of Asia would call it chi. So you have the 4 elements and then the spirit. I don't know what they called it in India, but whatever it is. 4, in different places they call it different things. They knew there was something. Today we know it as energy. It's energy. Today we call it energy. So schnapps, is just a really good way, I think, of remembering these elements. And what time is it? Oh, good, we have time. Hey, I'm reviewing all of chemistry in one period. I think this is great. You're getting a lot of science. All right, thank you. I'll take a bow later. All right, so what about these ions that we talked? So let's go back. Let's take a second. Let's do Cornell notes. We have all these details I just wrote. We talked about, what were the important things we talked about? Atoms. We talked about isotopes.
Half-life.
We talked about half-life. We talked about the structure of the nucleus.
We talked about stabilization, like stable atoms.
Right. So that's stable versus unstable, right? That's over here, stable. History, but I'm not. Do you think history was part of? Is going to be on your test? No, it won't be somewhere. I wouldn't. In history, you will not need to know the history. I give you the history for context. I give you the history to tell you why the scientific method is important. We would literally still believe the Earth is the center of the solar system if it wasn't for the scientific method. We literally had Copernicus burned at the stake. He was burned because the Christian church, I believe it was a Catholic church, said, no, this Earth is the center of the universe, you're a heretic, and they burned him. Galileo, they almost killed him. It's no crazier than anything else, guys. You cannot, of course it was wrong, but if you're going to challenge what people believe, they're going to get angry. Of course, let me pause this stuff. Yes, people still feel strongly about what they think is the right answer, and if you're on the wrong side, they're going to be, some people get violent. Like they do. It's not the right thing to do, but they do get violent. So it's not something, but that's just history to give you context of why the scientific method, why do we do this and break it down in what you guys would call boring ways in such a step-by-step process, because it's necessary in order to filter out all that. How can we filter all this noise out and still have a real discussion over what we can agree on? All right, so let me pause this. All right, so we also talked about the elements of life. Right, on this side. And these things called ions. So we have this thing called atoms. So atoms are just something that's defined, and the elements are defined by their proton number, correct? Yeah. We said it's defined by the proton number. Defines an element. And we said there's schnapps, those are the elements of life. Ions, though, we haven't talked about. What are ions? Ions are elements that have unbalanced charges. They're either positive or negative. What do we call atoms that have balanced charges? No, atoms / elements that are balanced, girls, are balanced, what do we call them? I heard it, neutral. So if you have hydrogen, a neutral hydrogen has what? One what? And one what? One electron. Does this talk about neutrons at all? No. It has nothing to do with isotopes. Nothing to do with the nucleus other than the number of protons. However many protons you have, if you have the exact number of electrons, then you have zero charge. Is that clear? That is a neutral atom. If you have, however, a positive unbalance, not you balance, but it's hard to write and talk at the same time, seriously. If you have a positive unbalance, what we like to do is we like to draw, or I like to do, is I like to do this.
Oh, what is that? Okay.
Or just the plus in cation. Or not cation.
It's like a cat.
It looks like a cat. That's exactly what it is, a cat. It's a cat, and that's what it's meant to be. And you can actually, what I would do when I was drawing in college, what I would actually do is do this. And I would draw that in college, and it would just remind me the plus sign, cation.
Look at the cute little cat.
I had nothing for an anion, nothing. I just is not a cation. And so it's
Like negative. I don't know. I just associate with negative. So.
I guess it's hard. Be careful, because then you got neutron, and it's like there's the N word again. Neutron, negative, neutral. Not. It just gets crazy. So, why is there so much laughing in this class all the time? I'm like, what am I doing? You're jolly. I think I'm being made fun of. I feel like I'm being made fun of 90% all day. Besides my spelling.
Sometimes you just say things that you shouldn't. Like that one Mayor.
The Maillard thing was hilarious. She was talking, I said Maillard.
No, I don't think that.
All right, let's move on. Unbalanced, positive cation, neutral charge is 0. However, if it's unbalanced and it's negative,
And he doesn't like it.
and it's negative, we call it an anion, and I have nothing for you and that just means it's a negative charge.
Okay, so it's like anion is like Annie doesn't like you, so it's negative.
Okay, whatever works for you. I just think cation is positive, and the other one's negative. That's it.
It's like, I don't know.
You guys do what you want. I just tell you, what works for me is I think a cation is a positive, the other one's a negative. That's it. Now, did I say anywhere in here, I said atoms and elements. Unfortunately for you all, there's also these cations and, guys, these neutrals, cations and anions also work for molecules. So molecules can also be neutral. They can be cations. They can be neutral. And they can be negative. Who can tell me what a molecule is? There's a bunch of seniors and juniors in here. All of you have had honors biology, chemistry, and or AP chemistry. What is a molecule? Go. Now. All things are made of atoms. Be specific.
More than one atom.
What?
More than one atom.
Combine in what?
Elements.
Yeah, more than one atom.
Covalent. Molecules. It's very specific. It's very specific. It's very specific. Salt is not a molecule. Please pay attention because you're going to run into problems because you don't understand the simplest of concepts. Molecules are covalently bonded atoms. Covalently bonded atoms. Anything that's bonded covalently is a. There's a lot of talking going on, Mayar. Sorry, I know I'm not supposed to say your name, but there it is. So molecules, covalently bonded atoms. I don't care. I'm explaining, so pay attention to what I'm saying. Blah, blah, blah. Pay attention. So if we look at a molecule that's negatively charged, we can look at oxygen sharing electrons with hydrogen. Gives you a negative charge, a -1 charge. So this is a covalently bonded atom, a molecule. It is a molecule. It's an OH, but it has an extra electron. A positively charged molecule might be something like NH4. I think it's +2. Ammonium. This is ammonia, I think. Somebody's gonna have to look up if NH4 is +2 or +1. I can't remember, and I can't do it in my head right now. It's +2. Okay. So then, of course, you got the neutral. That's oxygen gas.
It's +1, not +2.
Thank you.
You sound like such a nerd.
Stop picking on her. She is on it. Thank you. So it's +1 and -1 and neutral. Okay? Even though they're molecules, we call these polyatomic anions. Polyatomic cations. You should have had to memorize them in AP biology. I'm sure you did. And these are polyatomic
I think he meant AP
anions. I don't know the curriculum anymore. I know when I taught chemistry, I'd have my kids memorize it, but curriculums change. Maybe it's not, but there are a number of them you should memorize because they're so common, like peroxides, and there's just a lot of common molecules you should know. Anywho, how do you tell if something's going to be positive or negative or neutral? Well, you have to look at their valence shell electrons. And that's where the periodic table can be your best friend. So as I said a minute ago, your best friend is your periodic table. And your periodic table has at the top here, I will keep you after school if I have to repeat myself one more time. And I have evidence, since I'm recording, I have evidence of what you're doing. So I'm going to say clearly, one more time. At the top are the valence shell electrons, not in the middle. You can't trust these. These are d orbital atoms that are filling in the d orbital. They jump around. There's a good rule. You can follow good rule of thumb and figure it out, but we're not going to worry about these. The ones we're worried about are what? Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. Right? So they're over here and over here. So look, 1, 2, look here. 3, the ones place. 3, 4, 5, 6, 7, 8. 8 is a full octet. 8 is full.
The noble gases.
The noble gases. Everything else wants to be full. That's all you got to know for today. These are all the electrons in the valence shell. The ones place. Don't worry about the middle. They are d orbitals. They're confusing. pH in the food industry. If anybody missed it, it is posted. There's an online lab. So pH in the food industry. And they had these bacteria that could cause disease that grow, and they had you make sure that your food was at a specific pH. It's one of the reasons why you want to keep food refrigerated, obviously, to slow down bacterial growth. And these bacteria were growing on a plate, and they had, and you changed the various food in. So what exactly was it that you did? Please walk me through it. Yeah. Yeah, anybody?
We had salsa, and then we basically made a bigger batch of salsa, blended it up, separated it into 6 different things. It was 2 1As, 2 1Bs, and 2 1Cs, something like that. And then you test you get a pH tester.
Okay.
And you basically rinse it with water to make sure it's calibrated, and then you put it into each batch after you blend it, so it's homogeneous, and then you put it in the containers and test the pH beforehand, and then you add either vinegar or lemon juice, and then you basically increase the amounts on each one, and then your control has no extra acid in it, basically.
All right. And your objective is to make a formula that makes the salsa a certain acidity to reduce bacterial growth.
Ideally around 4.2 pH.
So the idea with pH around 4.2.
The salsa had an original pH of 1.6, so they wanted to
pH
because
original.
C-bond goes in 4.7 to 5.1 pH, so we need something less than 4.7 or 6 to prevent the growth of C-bond.
Sounds like people did their job yesterday. Excellent. And the lab report is not that important. If you just copy your notes, it's good enough for me. All right.
Oh, and also there's 3 samples.
Did I misspell juice, you said? I thought I spelled, isn't that spelled that way? Okay. Oh, okay. I was like, no, I thought I knew that one. Okay, all right. You guys are freaking me out with this spelling thing. All right, so what is pH? Anybody tell me what pH is? Level of acidity, okay. I mean, that's good, but is that complete? No. Level of acidity.
The higher the number, the more basic.
Excellent. So do we start with 0 then?
Yeah.
7?
And then, do we start with 7 then?
It's like a middle line. Number higher than 7 is base and lower than 7 is acidic, right?
So 7's in the middle.
Yeah.
All right. So 7's in the middle, and I go up to what? 14. And I go down to what? 0. Now, is it possible to get 0? Technically, yes. To get an acidity level of 0, it's more theoretical than anything. And is it possible to get a 14? Sure. 14 is easier than 0, but it's still an issue. Because what this means is pure hydrogen ion. So 100%. How you gonna do that? Like that, just a thing of hydrogen ions. That seems like. But yeah, you can get down to 0. There's some organic acids, I guess, is what I'm understanding is it can happen. So let's talk about what acidity is and what basic, and this is biology because this is a very important thing. In fact, hydrogen ions, mitochondria, just as this is not something you need to know right now. You should know it, but mitochondria have double membranes, and there's a hydrogen ion concentration difference between the two sides. So there's different acidity levels, and different channels allow hydrogen ions to flow from high to low. And that's what makes ATP in mitochondria. So that's going to be a hard conversation to have if you don't know what pH is and what is a hydrogen ion. So we discussed in an atom, in fact, one of the things we said the other day when we did meet is that hydrogen has only one proton. And if it's neutral, it has one electron. And we'll get back to pH in just a second. The problem with this is that this fulfills one of the two rules. And in 9th grade, I taught you this rule. And it is a rule that works. It's not, I'm not going to promise you it's going to work forever as you move on into college. But it's a rule that works. Is number one, when this idea that number one rule of bonding is the tendency of atoms to move toward being neutral. They want to be neutral. I use the word want very loosely because obviously they don't have a will. They might. Some physicists argue that everything has consciousness, but that's something Native American religion also believes in. It's theoretical. I just read the article the other day. Native American religions believe everything has a spirit, the spirit of rocks and trees, and so there's consciousness in some level with all things. Some physicists argue that that's probably true of all things as well, but I don't know. Anyways, as far as we know, there's no want. There's a drive towards neutrality. Okay, so things need, that there's a plus, it generally wants to have a negative. If it's negative charge, it wants to get a positive to be neutral. So the objective is it wants to move towards having neutrality. So for this particular drawing here, for this hydrogen neutral atom, that's checked off. We're good. But there's a second rule, and it's a big one, and it says a full octet. Now they use the word octet, oct because of 8, because most atoms on the periodic table, most of them, have 8 electrons in their valence shell. This has to do with the octet has to do with the valence shell. That outer shell. Now, the problem with hydrogen, and in fact every element, I don't even know what just happened. I think I undid that. The valence shell it's the outermost shell. And the problem with the first column, the period is the first column of the periodic table is that its outer shell only has 2 electrons. You can only fit 2 electrons. So the outermost shell of hydrogen can only fit 2. So it's not going to have 8. It'll be full though with 2. So if it gets a second electron, if it did that, then it would be happy, but then what would it be? It would satisfy the second rule. Did I just delete the whole number 2? Yeah. Is that what happened? Good Lord. I didn't do anything as far as I know. Well, I can't play with this thing. This app has been very glitchy and I don't want to mess with it. So the tendency of atoms
No, you wrote that.
Yeah.
It's on the top. Mendo.
Number two is
to move
Because I already wrote that down.
toward
You already wrote it down.
a full octet.
Oh, full octet rule.
All right. So at that point, we're talking. When we talk about octet, we're talking about the valence shell, which is the outermost shell. Remember, these aren't actual places in space. They're ranges of space, a probability range, because of the whole uncertainty thing. All right. So if it has a full octet, if it has this configuration, then it would fill out this one, but then it would lose this because this would have a negative charge. There's an H negative, and that doesn't exist. And one of the reasons it doesn't exist is when you calculate the forces involved in trying to attract a second electron and the repulsive nature of the electrons around this small orbital. There's not a lot of room for those two electrons to hang out. It's energetically unfavorable for it to happen. We can force it to happen with enough energy, but in nature, it doesn't often happen. So what we find is we don't really find a hydrogen that's neutral. I mean, that has a negative charge. It's not something that we find commonly. Yes.
So is it the protons? If the protons change, that makes it a new element?
Yes. Remember that's something from last time, that the proton number defines the element. So we can't change the number of protons, because if we add another proton, yes, we could have two electrons. We'd have more space. If we added another proton, you'd have to add two neutrons. And then you'd have another electron, you'd have a full octet. Yes, it would be stable, yes, but then we would call it helium. It wouldn't be hydrogen. So the thing about, that's where bonding comes in. See, chemical bonding is just a natural phenomenon happening that occurs because of these two realities, these two tendencies of matter. What happens is that a hydrogen atom that has a plus one, one positive charge, has one little electron in its outer shell, and in biology we usually draw only the electrons. We don't worry about the number of protons, not in the drawing. And here we have hydrogen over here that also has an electron in its outer shell. Then if they're able to share these electrons, then we say they would be drawn this way. We don't even draw the electrons really, we just draw lines. If we draw this, now this is hydrogen gas. That's very stable. That has a full octet and it's neutral. And because if I would draw the full number of electrons, where you have a positive charge with a negative around the outside. You have a positive charge with a negative around the outside. Again, I want to remind you that these drawings are not to scale. If I was to draw it to scale, there would be just a little dot in the middle of a large empty space, because remember, according to our model of the atom, atoms are made mostly of space. But we're not going to worry about that. This is biology. We're more concerned about how do these atoms react inside a body, inside a living thing.
Mendoza?
Yeah.
Is there like a certain, I'm totally blanking, it's like a certain word for when that occurs?
When what occurs?
When that right there, when two electrons
Yeah.
come together.
When they share, yes, there is. It's called a covalent bond.
Yeah, yeah.
This is a covalent bond, and what that means, it's the only real kind of bond. we do call ionic bonding ionic bonds. Those are used. Hydrogen bonds, right? We call these things bonds. But this is the only true bond. It's analogous to marriage versus boyfriend-girlfriend. All right? Like, is it a real bond? It's not. Yes, it's a bond, but it's more of an association. This is a true bond. They're sharing electrons. Very stable for the most part, compared to the other kinds of bonds.
What if they get a divorce?
Yeah, they do. That happens all the time. A hotter guy can come along, or girl, and we can draw that in this way. Oxygen come along. Oxygen's real cute. Oxygen has
Oxygen is, no. It's all I want.
oxygen is something a lot of girls want.
I think all
Very
of us-
hot.
No, I think all of us want oxygen so we can make.
So the way we do this, Lewis dot, these are called Lewis dot structures, and I'm sure you remember doing this in chemistry, but I'm going to do it here. Oxygen has six electrons in its outer shell. It has a total. Remember, oxygen has a total of 8. I keep talking about the outer shell. I want to remind you the shortcut. If you have a periodic table, you look at the shortcut. The shortcut is at the top of the column, the ones place tells you how many electrons in its outer shell. So if we look at a periodic table, I think I have one here somewhere. I had one in the other page. Let me see if I can find it really quickly in my files. If I can't, we're just going to move on. Oh, there it is. If we look at this periodic table here, oxygen is in the sixth. Here is in the sixth column. You see it? So it's in the 16th, right? But it's this six. The ones place is a 6. On a lot of periodic tables, they give it to you in Roman numerals or whatever. It's a really key, useful number because it tells you there's 6 electrons in the valence shell. Now, oxygen actually has 8 protons. Now, I'm going to do this for oxygen. I'm not going to do this for all the other ones because this is not chemistry. But there's 8 protons, 2, 3, 4, 5, 6, 7, 8. Oxygen has atomic mass of around 16. It's a little more than 16, but we're going to, or a little less than 16. What is it? A little more than 16. They round it up here. So we know it has about 8 neutrons, but we don't care about the neutrons because this is biology, except for when we're dealing with isotopes. It's really not a thing for us in biology because it's not your body. Has nothing to do with that. So we know that there's oxygen has 8 protons, and I just drew it, didn't I, somewhere? Oh, there, 8 protons. And so if we start filling them out, we have the first shell. They can hold how many? 2 electrons. That's the first shell, 1, 2. So this is the 1s. That's all there is in the first shell is an s. Then if we do the second shell, how many electrons do we have left to fill in? We have 6 left, right? We have to fit 2 more on the 2s. The 2s has 1, 2, because that's all I can fit. This is a 2s. But then there's a 2p as well, isn't there?
What are those little shells, right?
These are shells, yeah. So we got. There's 1 orbital. That's the z axis. There's the x axis. To me, it looks like balloon animals to me. Yeah. I don't know about you, but I don't think Ryan Reynolds has anything to do with this. It's kind of hard not to, and in fact, it's going to come out in the video. You can listen to it, I'm sure. All right, you can defend that later. Right now, I'd really rather focus. So there's all this space out here in the two P's. This is the two P's. So 2S, so in the two P's, we have two, we said, guys, I can't fight you on this. I'm going to have to separate you. I can't. There's eight protons, which means there has to be 8 electrons. And in order for it to be a neutral atom, if it has 8 pluses, it has to have 8 negatives. Understood? To have a full outer shell, did I say full outer orbital? I said shell, which includes the S and the P. So it's a little tricky. So when we look at shells, you're talking about all of, you're talking about all of this, the 2S and the 2P. This is the second shell. The second shell is a space within which the orbitals exist. The shapes of the orbitals are due to the geometric shape of the space that would allow these negative charges to exist together without pushing each other out of that space. All right? Like putting my brother and I in the same room would not be a good idea. So that's what would happen. That's what happens with these electrons. They generally push each other out of this space. That is, the 2S and the 2P are both in the second shell. The first shell only has an S. So understand, when we're talking about these shells, there's a shell and then there's the orbital. I don't want you to confuse them, because then it's hard to understand why there's actually why oxygen makes 2 bonds. So if we've already we've done 4, we need to fit in 4 more. So there's only 4 electrons in the p orbitals. So there's one. We would fill them in. What we do is you'll learn this. Oh my goodness. You go 1. Are you kidding me? Oh, this is my bad. 1 up. 1. You fill them all in the upper, all up first on each axis, and then the axes they're sharing, you point them, they spin downwards. So 1, 2, 3, 4. That's all you got. How many more electrons does it need to fill the outer shell?
4 more.
No. Say again? 2. You need 2 more. You need 1 here and 1 here. Now that's a lot of drawing. And I don't know about you, but there's a lot of bonds, a lot of atoms in molecules. There's a lot of atoms in just glucose. And then there's a lot of glucose in starch. So there's no way anybody wants to draw all this out. So we have to come up with shorthands that allow us to draw it. Yeah.
What is this? What is this
An atom, an oxygen atom.
What is the things on the
All right, so
Like the petals of the flower.
this is a p orbital. P orbitals are dumbbell shaped. The shape has to do with the energy requirements for that particular shape. If you're sleeping, I'm writing it down. Wake her up, because I don't want to have to write anybody up. I'm not allowing you to tell her to wake up. So p orbitals, those are p orbitals. Okay? Is that clear to everybody? So if I was going to draw them, and we will, and I am, then we would draw them this way. Instead of drawing all this, we'd say, okay, here's oxygen. It has 8 electrons, but only 6 in the outer shell. And I would probably, honestly, I'd probably use red for oxygen. So oxygen, we put the symbol of the element, and then we put the number of electrons. We start at the top, 1, 2, representing the order in which they would fill in, 3, 4, and I have 2 atoms facing each other. What I would do is make sure that the place where they're going to share is facing each other. So that's 1, 2, 3, 4, 5, and I need one more, 6. So 1, 2, 3, 4, 5, another more, 6. Now they each have 6. To have 8, they need 2 each. So they're not going to grab 2 more, but they can share this bond here, and they can share these 2 because they're unpaired. We call these unpaired electrons. So because they're unpaired, they can bond. And so what we get is oxygen with 2 bonds. And we call this oxygen O2 gas. This is the shorthand known as Lewis dot structure. This shorthand, each line is 2 electrons that they're sharing, is 1 covalent bond. When you see a 2, that means these 2 atoms are sharing electrons. There's 2 oxygens, and you have to assume they're molecules. If they say gas, it's a molecule. And this is an oxygen sharing 2 bonds. You should be to the point, by the time you get to college, if you're not, you will by the time you get out of college, you should be able to look at oxygen and say it needs 2 bonds. If it's going to be bonded with an oxygen, it's going to have double bond. If it's going to be bonded with a hydrogen, it's going to need this, it's going to need that. And it should be easy in your mind. Hydrogen, however, if we look at hydrogen, do the same thing we just did with hydrogen. Let's use black for hydrogen. And with the models that we have here, we have some models that we're going to use. You're going to build these molecules using plastic spheres and plastic sticks to symbolize the sharing of electrons. One set of models is our Mr. Dugan brought in his models, so you're going to make sure we take care of those models well. So anyways, hydrogen also only has 1 valence electron. It needs how many to fill its outer shell? It needs 2. And of course, it'll make a bond, and that's fine. But now when hydrogen meets oxygen with a small spark, you just need a little spark to give it a little jiggle, a little push. What happens is the hydrogen and oxygen, hydrogen would rather be with oxygen. Oxygen is much more electronegative. Whereas I was joking around a minute ago, I said oxygen is a lot prettier. Oxygen is a lot stronger. This is all about the pull on those electrons. Oxygen will pull much more easily on those hydrogen atoms. It's so energetically favorable for this to happen, for these 2 to break up. And in 9th grade, we did this with some batteries. We separated hydrogen and oxygen. We separated water, made hydrogen and oxygen, and we blew them up and made water again. I don't know if you remember that, but we did it. I do it every year. If I didn't do it with your class, I don't know why. So hydrogen and oxygen come together, and we call this electrolysis. It's in your book. They talk about electrolysis in your book, and so they're breaking up water. But when oxygen is sitting there with its 2 missing spaces, now here's hydrogen needing 1 space. What it forms is, I think it's obvious to you, I hope it's obvious to you, it forms this thing. What is this thing? 2 covalent bonds. The molecule is called what? H2O, or water. Water has a specific shape. It's a tetrahedron. The reason it has this shape is because these electrons, these pairs of electrons, push more. They're much more repulsive, much stronger push against these electrons than these 2 are to each other. So it squeezes them together. So have you ever used those hand grips where you practice your strength to get strength in your grip? So it's a lot like that. You're squeezing them together. And the reason they're getting pushed is because these are stronger and they're pushing into making this shape. This is called a tetrahedron. There's a lot of reasons why that's important. We're going to talk a little bit about that today. So water is obviously one of the first molecules that's going to be essential for all life on Earth. There is no life on planet Earth that does not require water. Even the little tardigrades, those tiny little water bears, they need water. You've never heard of the tardigrade? I can't believe you've never heard of it. Has anybody heard of tardigrades? Yeah. What have you heard about tardigrades? Oh my God. You two are going to give me a headache. I'm going to have to separate you two just so I don't kill you. So tardigrade, what have you heard about tardigrades? They're tiny. I don't call them ugly. I think they're really cute. It's like pudgy little bears. I'll pause it and show you. So it's also called the water bear. The interesting thing about these things is they live in any environment. You can put them in, you can completely desiccate them, take all the water away, and they just shrivel up, and then you put water back in, and they pop right back to life. It's I don't even know how long they live. They're just incredibly little creatures. They're microscopic.
They don't die.
Did I say that? I said I don't know how long they live. Oh, they're not dead when you take away all the water. No, they don't die. We've sent them to space. They're alive. They freeze them solid. They live. Like they're incredibly hardy little. Someone was jokingly over saying they're special, but they are very special.
I think he was talking about you. I didn't say that.
What somebody said over here. I don't know. I don't know who said it. I think they're incredibly cute. When you consider bacteria. Here, okay, it does look a little fake, but listen, what's really cool about this thing, it is not, look, stop. You drive me crazy, stop. It is not AI. This actually looks like what it is. It does look like this. It's real. You can take photos of it. You can see it under an electron microscope. You can look at them. They're everywhere. They're in water. You probably drank them before. It is incredible. They're incredible little creatures. You eat millions of little creatures you don't even know exist. You sleep. Oh, there's so many things you don't know. You have a whole ecosystem living on your skin. An entire ecosystem.
Hey guys. Okay, I think the topic changed. Let's go.
So when we look at these creatures, stop judging them. They're a necessary part. They're a necessary part of our ecosystem. A necessary part of our ecosystem. Without them, that's fifth period. Okay, I'm just saying that. Just make sure you're in the right period. So when we're looking at these little tardigrades or whatever, there are real implications to this. They're necessary. When people use bleach, those OCD people are constantly washing their hands, they make themselves sick. They start to bleed. They start to get other things that are much worse, staph infections, all kinds of other things that happen that will kill you. These guys live with us. They're helping us. Now, what happens to some people is they become allergic to the dust mite poop because they poop on our skin as well. The dust mite poop becomes a problem. These guys, I don't know what they eat. You can look up the ecology, what these guys do. They look like they're eating really tiny things. They obviously don't have eyes because they don't need it.
Is that really their mouth?
Yes, that is their mouth.
Yeah, it looks like a vacuum.
Okay, whatever. I'm just saying, bottom line is, I don't know what these guys eat, but everything has a purpose. All creatures have a purpose. If they don't have a purpose, they're quickly nixed from the environment. Parasites, you might argue, the only thing that you might argue, why is a leech around? But they actually have a place in the ecosystem as well. Yeah. Mosquitoes are an important part of the ecosystem. They feed fish. They're a real big part of the food supply for fish. Without mosquitoes and insects like them, they just wouldn't. I mean, that's sad to me because I hate mosquitoes. But without them, it would be a big problem for the fish. Flies? Oh, same thing. Flies are really incredibly important for spiders and for each part of the ecosystem is important. And as you move up, a lot of people think bears and tigers are important. They are, but so are spiders and insects. Insects, in fact, there are more insects than there are any other kind of creature on planet Earth. By biomass, obviously plants and algae, photosynthetic organisms are number one. But of animals, insects are the largest portion of life on Earth. So when we say, who cares, insects are dying, you should care. Without insects, we don't have a lot of what we need to grow our foods. They're much more important than we are. If humans disappeared tomorrow, planet Earth would go fine. Insects disappeared tomorrow, planet Earth life on Earth would have a hard time moving on. In fact, I would argue life would do better without humans, but that's another story. Life on Earth, obviously humans wouldn't be any better. We'd be worse off, but... All right, so water. Now pH. What is pH? pH is equal to the negative log of the hydrogen ion concentration. Why is this portion of the equation so important? Does anybody know what log is? What is... Yes, it's... Yeah. So, why is log so important? What is log? When you take the log, the first thing you should know is there's different bases for log. So when we say log, we mean log base 10. You can do natural log, ln, which is log base, it's still log, but the base is 2.8 something. I forget what the natural number is. I'm assuming you covered this in math? You should have covered it in math. Log base 10. So when you take a log of a number, you take a log of anything. Let's say it's a log of 100. Log base 10 of 100. Then what you're asking is, the question you're asking, and let me not put equals because equals can confuse people. So say what you're asking what number do I take the base, which in this case is 10, to what number do I take 10 to equal 100? So when I take the natural base log, the 10 base log of 100, I'm asking what number do I take 10 to be 100? The second power. So log of 100 is 2. That's easy, right? A log of 1,000 is what? 3. Now, not that this is important for right now, though you will see natural log come into the growth formulas. But this is the same thing. Everything is the same. Instead of taking 10, you're doing what? Take 2.8 whatever to x to get 100. So that's something you need a calculator to do unless you're really a genius. I mean, I don't know what else. I can't do that in my head. So you can do that with a calculator. But log base 10 of any 10 factor of 10 is easy, right? Which is going to get us to, this discussion is going to get us into scientific notation real quick. Yeah, you need to know it. Because one of the problems is some of you had on FRQ was what is this 10 to the third, 10 3, negative 10 to negative 0.0124996? I don't know what this is. So it's just exponents and scientific notation. So log base 10 of 100 is 2. Why is it 2? Because what number do I take 10 to equal 100? So if you think about it, if I'm taking the log, and then remember when we take the log, what we're saying is what number do we take 10 to log of the hydrogen ion concentration? Let's do a little algebra. Let's find the hydrogen ion concentration at a pH of 3. What is the hydrogen ion concentration? Well, it's the negative 3. That would mean the pH 3 is equal to negative log of the hydrogen ion concentration. Which means I have to move the negative to the other side, correct? So I take negative 3 is equal to the log of the hydrogen ion concentration. And so now I have to take the anti-log, the inverse log, to get rid of log. I take the inverse log of both sides. And there's a little button on your calculator that says inverse log. You do inverse and then you do log usually. And you do the inverse log here. So the inverse log of the negative 3 is equal to the hydrogen ion concentration. So what is the inverse log of the negative 3? Who can do it? Who has negative 3? Who has a calculator? Do the inverse log of negative 3. Give me the calculator. Bring me the calculator. I can't believe you guys are going to be in chemistry in college in no time, and you're going to be doing this. You're going to be like, what's going on? In this case, there's no inverse. You do second, and you'll notice there's ln there, and there's 10 to the x. So 10 to the x, so you do negative 3, and you do 10 to the x. Oh, I see. This calculator's a little different. X, negative 3 equals is 0.001 equals the hydrogen ion concentration. So what they're saying is if you took 10 to the 0.001, that would equal negative 3. If you took, so do the inverse of it, if I took the log base 10, I should say. Yeah, that's right. So if I took the log of 0.001, or if I took 10 to the 10 to 0.001, I would get negative 3. 10 to the 0.001 I would get negative 3. Does that make sense to everybody? So the point is that's a very small number. Negative 3 means it's a very small number. The more acidic I get, what if I had a negative, what if I had 0? What is 10 to the 0 power?
1.
So 10 to the 0 power equals 1. So that means 100%. So that's why when we looked at the pH scale and we said, look, if we have a pH scale 7 is neutral, 0 is difficult to get to. Why did I say 0 is negative is hard to get to? Because that would mean 100% is what? Hydrogen ions. The concentration of hydrogen ion will be 100% hydrogen ions, and that's very difficult to get.
And what was
Now, that's a good question. So at this point, what we're talking about is this water again. There's 3 definitions of acids. Have you learned all 3 in chemistry? So there's the Arrhenius definition of acids and bases, where you have hydrogen plus. If it's an acid, there's a lot of hydrogen ions. If it's a base, there's a lot of OH negatives, hydroxide. So this side is high in hydroxide, OH negatives. And on this side, it's high in hydrogen ions. And I'm going to put these little square brackets, which means what? Concentration. So, which also means this is what? Low in hydrogen ions. And this is low in hydroxide ions. And Arrhenius was one of the first people to kind of define what's going on here. That's why it's called the Arrhenius definition of acids and bases. When we look at water, it turns out that water is neutral, H2O. The pH of H2O equals 7. Pure water has a pH of 7. And pure water, what happens to pure water is that water is in equilibrium. So it moves in both directions, and the equation moves in both directions. It turns out it can be H plus OH negative, and then it can be water. And because it's constantly doing this flip-flopping back and forth, it's constantly doing this. It's making water, then breaking out, making water, breaking out. The concentration of OH minus and H plus is equal. So that's 7. So it turns out that the chemistry of it is very simple. Water's neutral because they're constantly switching back and forth. The other interesting property, so I've listed 2 properties of water, so 1 property of water for sure, water, that you have to know. You have to know these properties. They will test it on the AP exam in various ways. Pure water is neutral. Pure water is an insulator. If you have pure water, it will not conduct electricity. Isn't that interesting? But why do you not want to use water as an insulator? Have you ever dealt with pure water? No, you've never, even double distilled water is not pure. If there's even a little bit of ion, just a little bit of salt in there, it will conduct electricity very well because it's fluid. It's not the water that's conducting electricity, it's the ions, and the water makes it soluble, so it's fluid. Now the electricity can go in every direction, but the electrons are jumping not between water molecules, but between the ions dissolved in the water molecule. But water itself is an insulator. 3, another important aspect of water is it's really good, it's a universal solvent. Another reason why water is so important to life on Earth. There is no life on Earth without water. Yes?
If water is neutral, then what is alkaline water?
It's water that has hydroxide in it. And acidic water is water that has extra hydrogens in it. How did you get that? You added a chemical. But remember, it is very difficult to get pure water. Pure water is literally considered an industrial solvent. It is regulated by the federal government. It's hard to make. It can be dangerous if you drink it because it will literally dehydrate your body. And what you'll get is your tissues, all the salt, and then the water following would go flowing into your bloodstream. And you'll just quickly become sick. Like you don't want to drink pure water. It's just difficult to get pure water. That's all. It's really hard to make it. So it's not. You will not. Distilled water is not pure water. They don't say pure water on those bottles. They say purified water. It's cleaner. It's less minerals. Mineral water, I think Deer Park is a mineral water, is that right? What does it say? Spring water. Spring water is literally water with a lot of salt in it. This has a lot of salt. This is all the salt in every rock where this spring came from. It doesn't taste bad. It tastes good. Water has no taste. This tastes, water, pure water has literally no taste. What you taste in here, when you drink tap water, you're tasting the chlorine in the water and the fluorine in the water. We add chlorine and fluorine to kill bacteria. This, what you taste, is the minerals in the water. The potassium, the magnesium, the sulfur. Anything that's in the ground where this water came from is in the water at very low levels, but it's in the water. That's why this is a good conductor of electricity and what gives it its taste. Mineral water gets its taste from minerals. That's called mineral water. Yeah.
Does reverse osmosis get rid of the taste of things?
It does. It does. But reverse osmosis is a way to purify water. It just costs a lot of electricity. So we get rid of salt by, and we'll talk about reverse osmosis when we talk about osmosis. But it does. It gets rid of a lot of the minerals, but most of the time we still have some minerals left. So just a little bit in the water will make it conduct electricity. Do not think that you're safe because you have pure water. And as soon as if you had a bathtub of full water, I still would not get in it with an electrical wire. Because as soon as I stepped in it, what's on you? Salt. And as soon as your sweat is full of salt. You know that if you ever sweat a lot, you'll feel the dried salt on your forehead. Those of you that run, I know I used to run. When I was done running, I would literally have a crust of salt on my forehead. Anybody that truly exercises knows this is true. If you've not experienced it, you have not truly exercised. I'm sorry to say this, but you have to actually sweat to exercise. But I don't sweat when I exercise. Then you're not exercising for real. You're not. You're doing what I do, but you're not pushing your body. Your body could go further and you're just not pushing it. Or you're sick. You need to see a doctor. Because if you're not sweating, you got problems. You're going to overheat and you could die. So some people do have problems sweating. That is a real problem. So you have to really consider sweating is a really important part of thermoregulation. Without sweating, I know people think it's gross, but it's actually 100% healthy.
You gonna upload that?
Yes. If you're not sweating, you got problems. Farting is another thing that people think. I had a colleague who said to me, we used to meet at the pub and have dinner, a bunch of us, and we were having dinner, and she said somehow farts came into discussion, and she said she's never farted.
What?
And I said, oh, you mean you faux pas because you're a lady, you don't fart. No, she says she's never done any passed gas in any form. I said, dude, you got to see a doctor. I was dead serious. Because you should definitely be farting. If you're not farting, there's something wrong. Like, I don't know what it is. But farts are normal part of your body function. And she went to the doctor. She actually did have, I forget the issue. She had an issue with her intestines. So there are things that we all do. We all poop. We all fart. We all sweat. We all have snot. We all have earwax. Like, this is stuff that happens for a reason. If it's not happening, you got a problem for your health. So it's all funny until you're sick. So anyways, universal solvent. And what that means is it will dissolve just about everything. A lot of stuff. Obviously, it will dissolve polar substances easier. Because it is polar, because that's another property of it. It's polar. Water has a high ability to absorb energy. It absorbs a lot of thermal energy without going up in temperature. What is that called? Those of you that remember chemistry, the ability of something to absorb energy without, and how much something can absorb before it raises its temperature.
Is that its specific heat capacity?
Specific heat capacity. High specific heat capacity. And that's because it's polar. Polar substances have a high heat capacity. And it being polar means it's liquid at room temperature. Now this is all related to another. If it wasn't polar, it wouldn't have a high heat capacity. So sweating would not work as well. If it couldn't absorb a lot of heat before it turned into a gas, we'd have to lose a lot more water for us to cool off. That would really suck for us. Which means we have to drink a lot more water. We have to get rid of heat. How do we get rid of heat? We sweat. Dogs pant. But what are they doing? They're evaporating water. They also sweat in their feet. You'll see other animals, birds will pant. They're all getting rid of heat. How? By evaporating water. If it wasn't for water's ability to absorb heat and not increase temperature, if it increased temperature as soon as it gained heat, then what would happen is it would take less heat to evaporate it, which means you have to take a lot more water to cool you off. Very important consequence of it. Everything has consequences. So liquid at room temperature, that's important. The fact that we have liquid water is a big deal. There are planets in our solar system, there are planetoids in our solar system that have a lot of water in them. Their comets have a lot of water. It's useless for life. Why? It's frozen, it's solid. Solid water doesn't help life happen at all as far as we know. Life as we know it only exists in liquid water. Solid water, it's either suspended, like in the tardigrade, life is suspended, or it doesn't exist at all. You have to have liquid, and things have to be able to change. So 7. Water is less dense when it is solid. That's a big deal. This is one of the reasons life exists on planet Earth. Who can tell me why life exists on planet Earth because of number 7? Yeah.
Because the density of ice is less than water, and it allows the ice to flow on top, so life won't get crushed.
That's right. It won't freeze to death. So fish, do you ever wonder what happens to fish in the wintertime? They don't freeze and unfreeze. Frogs, you ever think about snails? Like during the winter, everybody's all cool looking at the little minnows in the lake and the stream. And, oh, look at the baby fish, how cute. Look at the turtle. Look at the baby turtle. Oh, look, it's eating. Oh, cute. Little frogs. But wintertime hits, where are all these things?
They go outside and hide.
Hide where?
Fishes or animals?
Yeah, where are they hiding?
I mean, fishes are animals.
Under the ice. They're in the water, asleep. The fish are actually awake. They're still hunting. They eat, but they just slow down their metabolism. So people go ice fishing. They're still hungry.
I thought water has no
You thought water had no density?
Ice?
I don't know of any matter that has no density. The water certainly has density. It has less dense. It's less dense as a solid. which is really weird. Almost everything else, if you take the solid form and you put it on the liquid form of that substance, the solid form will sink. Almost everything you know of, mention it. If it can melt, if you took the melted version and put the solid, like gold, take molten gold and put a gold bar on top of it, that gold bar will sink. Like things sink, but not ice, not water. Yeah.
What's the reason why it's less dense?
That's a good question. And that actually brings us back to this drawing of the water molecule. The reason I mentioned that it's a tetrahedron. And the idea of hydrogen bonding. So what happens is water has this really specific shape. It's spread out. You see how it's spread out? The hydrogens are spread out? So when water comes along, it has these two sides. As a positive side and a negative side. This is the negative side, this is the positive side. When you take a bunch of these together, and obviously a lake or a stream or whatever is made of water, take a bunch of these together, and what's going to happen is they're going to line up so that the positive side points at the negative side. And because they're all spread out, as they become solid, they get closer together, as all solids do, but they can't get any closer than this. They can't form a very dense object because they can only get this close.
There's no space like, oh, there's.
So they form, that's why water makes snowflakes. You've seen snowflakes? What are they? Spread out. They're all spread out because as they go from liquid, remember in the liquid form, when it's liquid, these molecules can roll around and kind of come in here, then that pushes that one out, and then this takes its space, and they can get much closer as a liquid because they're rolling around, turning, they're pushing each other, they're hitting each other like billiard balls on a pool table, so they can get pretty close to one another. But as they slow down, as they have less kinetic energy, which is what lower temperature means, right? Less kinetic energy, they have to settle into a position. That position is one which is spread out. So the liquid form is therefore much less dense than the solid form. And so what you get is the most dense form of water is just before it freezes, at its coldest temperature right before it gets to zero. Once you get to zero, it turns into a solid and spreads out. So that's really strange. Most solids don't do that. If you look at sodium chloride, well, that would be a bad example, but if you look at gold or silver, what you would see is, I'm just going to put just red dots because I'm not going to put AU all over the place. Solid form looks like this. They're real close together. That's what you learned in middle school, right? Didn't you learn that in middle school? I hope. A solid means they're all packed together, correct? Less space in between the molecules, which is still true. The water molecules do settle down and pack, but they can't pack any tighter than they do because of hydrogen bonding. In the liquid form, they're spread out a little more. And the gas form, they're spread out the most. I don't even know why you're here. That's not cool. They're spread out even more. So this is a gas, this is a liquid, and this is solid. And that's normally the way you were taught in middle school. And it's still true. It's just that water, when it packs up, it packs in a spread out way. All right, you can't. It's because of their shape. It's because of their shape and the fact that they do hydrogen bonding. Hydrogen bonding is a weak force that only becomes important when it's at lower temperatures. The lower the temperature, the more important hydrogen bonding is, because it's not really at low only important, but it becomes more important at low temperatures because there's less kinetic energy. As long as you have enough kinetic energy, it might bond for a second, but then it releases. It's not that big a deal. But when you get cold, but it's also why water, it takes so much to make water into a gas. Why does it take so much energy to melt water? It takes a lot of energy to melt water. If I made a graph, if you want to do the lab, we can do the lab where we melt the ice and then boil the ice, the water, and see and measure the temperature as it's increasing and see what happens as we keep adding heat to the graph of the temperature. We can do it. I can tell you what is going to happen, what should happen unless something's wrong. What should happen is as you increase temperature, as you increase heat, you keep adding heat in this direction, the temperature is going to increase. Does that make sense? That makes sense. I increase heat, temperature goes up. You got to remember, temperature is a measurement of average kinetic energy. It is not a measurement of heat. Is that clear? You got to put that iPad away. I don't know what you're doing, but it's not this. I don't know why you're smiling. So as I increase heat, though, temperature, kinetic energy increases. So we go up. So what happens is as it keeps going up until a certain point where it doesn't. So if this is ice down here, let's say this is 0. This is all, and notice I'm annotating the graph. This is annotating the graph. Over here, it's solid. Water's solid. This is for water. Phase diagram for water. I keep increasing heat. At some point, this would be wrong. At around 0, I would keep the ice would not change its temperature. As long as there's ice in that cup, the temperature itself does not increase. It flatlines. Even after this is 0, this is not 0 degrees. This is 0. This is 0 heat. All right. So as I increase the heat, at some point, when I get around 0 degrees Celsius, this is in Celsius. At some point, what's going to happen is it's going to flatline. And I'm going to keep adding heat, but the temperature's not going to go up. That's because if there's any solid in that beaker, if we have a beaker with ice cubes in it, if there's any ice in there left at all, what is happening is the hydrogen bonds have to be disrupted. You have to break apart the hydrogen bonds. So all that energy is going to breaking apart the hydrogen bonds. It will not go to increasing the movement of the vibrations of the molecules. They're all going into breaking the hydrogen bonds. Until finally those bonds are broken, then it starts to increase temperature again. Then what's going to happen when it gets near 100 degrees? It flattens out again. Because in liquid water, it's going to hold its temperature because the hydrogen bonds are holding it together. In order to get the temperature to go up, can we get off these computers and take notes? The hydrogen bonds are going to, they're not going to increase temperature until all the hydrogen bonds are broken. So then after that's true, after it's all gas, then it increases temperature again, and it can go up, and then there's other phases of matter I'm not going to discuss because they're not important for life. And that angle's a little stiff, so I'm going to just change that just to be picky. So this, obviously, at least I hope it's obvious, this is going to be this where it's solid. This is where it's liquid. And this is where it's gas. So would you rather be burned? Let me rephrase that. Yeah. Would you rather be burned with water at 100 degrees Celsius, or by boiling water, or by gas at 100 degrees Celsius? Steam.
You asked this freshman year.
I did.
You did.
I ask it all the time. Which would you rather be? You know, so hold on and let people think for a second. Would you rather be burned with steam at 100 degrees or liquid at 100 degrees? It's the same temperature, she says. Wouldn't it feel the same? It wouldn't be the same, because look at the graph, look at the table. When you're looking at gas, I'm going to do the gas in yellow. Actually, let me do the liquid at yellow. Liquid at 100 degrees Celsius only has this much energy. Liquid at 100 degrees has this much energy, whatever this number is. Okay? That's how many joules of energy would go into your body if you got touched with water, boiling water. Gas at 100 degrees would have all this energy plus everything that came before it. Would have this amount of energy. Even though they have both the same temperature, look at it, they're both 100 degrees. Gas will to give you the energy it has to be a gas. It will become liquid. It'll go from gas to liquid, and your body will absorb that energy. And so you'll absorb all this energy plus all this energy, and your burn will actually be worse. Not to mention the hottest, assuming that the pressure is 1 atmosphere, assuming you're not talking about, you've seen pressure cookers, right? Where you put, assuming you're not using a pressure cooker, then water can only get up to 100 degrees. Liquid water can only be boiling. It's its hottest it can be. Steam can be thousands of degrees. It doesn't have to be 100 degrees. That's how the pressure cookers work. You increase the heat. Water, if you're boiling something, all you can do is give it 100 degrees worth of kinetic energy, 100 degrees worth of heat. It will not, all that heat's going to go, but it's only 100 degrees. Steam in a pressure cooker, that heat you keep increasing, all that heat goes into the solution, into the substance. It's all liquid, but it's all gas, so now you're getting a lot. By increasing the pressure, you're able to get water to go up. So that brings us to another property of physics that you should understand. There's two things that determine if something's going to be a solid, liquid, or gas. What are at least two things? Solid, liquid, and gas. This should all be a review of middle school or elementary school math, science. Solid, liquid, or gas. This is elementary school stuff. I can pull it up, 3rd grade work, 4th grade work. I'm not even kidding. It's based on that. Obviously, it's a little more complicated, but it's based on. I'm not being sarcastic or joking. It's like 3rd to 5th grade, something like that. I guess that comes with. Are you smarter than a 5th grader? Yeah. Kinetic energy. So the amount of kinetic energy is going to be important. KE, remember the energy of movement, which equals 1/2 mv squared.
Oh, I think I remember this.
You should remember this from 8th grade, 7th grade, 6th grade. That's right. But how close they are is determined by how much kinetic energy. Look, if you guys are all moving around, you're going to be pretty far away. If you're moving out really fast, what's happening to you? Or you're going to be what? Be further away, right? You can't get too close if you're all running in different directions, right? So you're going to get further. The faster you're moving, the more further away you are from each other. The slower you're moving, the closer you get. That's why solids are more dense than liquids. That's why gases are less dense than liquids. Because they're moving, the reason they're further apart is they're moving faster, the kinetic energy portion. But then there's another thing, and that's pressure. So that part was middle school. This part you should have learned, but you may not have. I can almost guarantee you learned the top part. This part I'm almost guaranteeing. I can't imagine you went to middle school and didn't learn this. Do you remember it? I don't know. So pressure though means that you're squeezing things together. Squeezing. You're putting pressure on things from all sides. So when you're squeezing things together, they're going to want to be close together, right? Correct?
They want to be far away.
They want to be far away. They're pushing. They're trying to get far away. They have enough energy to be away, but are you allowing them to be away? No, you're restraining them. You're pushing them together. So as you increase pressure, you move towards the solid. And it's a balance between these two things. I could make between temperature, which is a measurement of movement, of average kinetic energy, and pressure. It's a balance between those two things that allow the stuff to be solid, liquid, or gas. I could take a bell chamber. I have the chamber, but I don't have. I have the air pressure, the pressure, the vacuum pump, but I don't have the bell chamber. I could take a bell chamber and I could make water boil at room temperature. I could turn it into a gas. I could take a pressure, add pressure, and I could take oxygen gas. I could turn it into a liquid. I can turn oxygen gas, and turn it to liquid at room temperature. How do I do that? I add pressure. I just keep pumping gas into a small space. You know this if you've ever seen scuba divers. Scuba divers in their tank have liquid oxygen. If you've been to the hospital and you've seen those oxygen tanks, or those hydrogen tanks, or those CO2 tanks, all those, you've used CO2 pistols, haven't you? Those little cartridges of air, the cans of air. They say can of air. Huh? Yeah. They look. They say air. You can go to the store and buy a can of air. It's liquid air. They took air and they pushed it. They squeezed it together until they made a gas. When you release it, it gets really cold. Why? Because you're not allowing the molecules to move very much. When you release them, they start moving. Where are they taking the energy? From the surrounding environment. So anything that's touching it, it's going to absorb that energy and take off. When you release that air, the can gets very cold. So these are all related to one another. They're important ideas that you should have learned in middle school. Certainly the solid, liquid, gas part, but now we've reviewed it. So now when we have these discussions on oxygen, on bonding, I think we have a good sense of what we're doing. So come in tomorrow ready to start doing covalent bonding in molecules.